we've gone ahead and have drawn a free body diagram representing the forces acting on the lamp, which is hanging vertically from a cord in a descending elevator. There are only two forces acting on the lamp. There is the tension in the cord that's pulling up on the lamp, and then there is the lamp's gravitational force pointing down, which we've labeled mg. Now, we know from Newton's second law that the net force acting on the lamp is equal to the mass of the lamp multiplied by the acceleration of the lamp. Now, it's important to understand that the elevator and hence the lamp is descending. So what this means is that the velocity of the lamp is pointing downward. However, we are told that the lamp is decelerating, which basically means it's slowing down. Now, in order for any object to slow down and decelerate, the acceleration vector has to point in the direction opposite to the velocity vector. This is the only way in which an object can decelerate. Of course, if the acceleration and velocity were pointing in the same direction, then the object would accelerate or speed up. But basically, since the question says that the lamp is decelerating and the velocity is pointing downward, this must mean that the acceleration is pointing upward, and hence the acceleration is positive because it's pointing upward. So when they give us this value of acceleration of 2.4 meters per second squared, we're going to have to use a positive value. So keep that in mind as we progress. Now we turn back to Newton's second law, and we have the net force. So there are two forces, again, the tension and the weight or gravitational force of the lamp. The tension is pointing upward, so it's positive, and then we're going to add that to the weight or gravitational force, which is downward, so that would actually be a negative mg. And again, this will equal the mass multiplied by the acceleration. Now we are adding a negative, so of course we can simplify that and write T minus mg is equal to ma. We want to solve this equation for the mass, which is what we're being asked for. So let's add mg to both sides of the equation. They'll cancel out on the left side. We now have tension equals ma plus mg. Continuing to solve for mass, what we'll do is factor out mass on the right side. It's a greatest common factor. So we can factor out m. This leaves us with a plus g. And then finally, we will divide both sides of the equation by the quantity a plus g. So we can see that tension divided by a plus g is equal to the mass. The question stated that the tension in the cord was 89 newtons, so we can fill that in, divided by the acceleration, which we argued earlier would be a positive 2.4 meters per second squared, plus g, which of course is the gravitational constant, which has a value on Earth of 9.8 meters per second squared. So you would go ahead and add the quantities on the bottom and then divide 89 by that value, and when you simplify that, you will get 7.3 kilograms as the answer for the mass. This would be the correct answer to part A of the question. We now move up to part B. What is the cord's tension when the elevator ascends with an upward acceleration of 2.4 meters per second squared? Well, this question is telling us directly that the acceleration is upward, just like it was before. So the acceleration is once again going to be a positive 2.4 meters per second squared. This time we're solving for the tension. So we go to part B, and we can actually return to our Newton's second law equation that we derived earlier. This one right here, tension was equal to ma plus mg. Now we're going to use the mass that we obtained in part A of the question. Presumably the mass has not changed, so we have 7.3 kilograms. Again, the acceleration is upward, so it's going to have that positive value. It's 2.4 meters per second squared plus the mass times g. Now, of course, when you punch this into your calculator, you're going to get the 89 newtons as the correct answer to part B. This should not be surprising because the acceleration in part B was the same as the acceleration in part A, and we used the same mass that we had obtained from part A. So the tension would come out to be the same value.